Writing an acid dissociation constant expression. So generically, for any kind of acid, it's going to donate an H plus. So I'm going to just use an H for what's going to be the H plus, and A for whatever the rest of it is, whatever the anionic component's going to be. So your weak acid is going to donate a proton to the water, which is in the liquid state. And I'm going to leave space. I'm going to put my equilibrium arrow in there in a minute. So once the acid has donated its proton, what is left behind is the conjugate base. So it's lost an H and a +1 charge. So it's going to be whatever the rest of that acid formula is with a minus sign. And then the water will accept the proton. So upon accepting the proton, we're going to add an extra hydrogen, so H3O, and then it will also gain a +1 charge from the proton, and that will be AQ. And you know what I'm going to do to make this absolutely crystal clear is I'm going to put those charges up on this line here. But I'm on my Mac, so I have to guess what my cursor is. Something like that. So there's my -1, and then a +1 there. So let's make that a little bit prettier. And yeah, obviously the 3 in the H3O will be a subscript as well. Let me draw a funky arrow, if I may. So here's going to be my, oh, it's purple. I like purple. Start wearing purple. Let's see if I can make this blue so it doesn't look weird. Okay, that way and that way. So there's my equilibrium. So that's for a generic acid-base reaction, right? So the proton is being donated from the acid to the water, like so. Okay, so for my acid, then I have hypochlorous acid. So that's HClO, and then that will donate a proton to the water. So what do I have left after I've lost a proton? I'll just have ClO minus, the hypochlorite anion, and then the water accepts the proton to form H3O plus. Okay, so again, I can put my equilibrium arrow in and make it look pretty. So to draw an acid dissociation constant, and it's the same for bases as well, what you've got to remember is the rules of heterogeneous equilibria. So water is in the liquid state, so it's not going to appear in the Ka expression. So for any weak acid dissociation, you're going to take the products to the power of their stoichiometric coefficient, which, as you can see in this case, is 1. So that makes things a lot simpler. That's often going to be the case for acid-base equilibria, dissociation constants. And then it will just be the concentration of whatever the weak acid is on the bottom. So this is 99 times out of 100 what your Ka expression is going to look like, and then that will be just equal to whatever the number that Ka is. So for our hypochlorous acid then, products will be the hypochlorite anion, ClO minus, and then hydronium cation, both aqueous, divided by my weak acid, which was the hypochlorous acid. So that's what my Ka expression is going to look like. And that's all there is to it, really. Yeah.